There is another type of bonding that we're going to investigate called covalent bonding. Covalent bonding comes from the sharing of electrons, and there are no ions that are formed, so there's no charge.
Now what we're going to do, we've been looking at compounds that are ionic, and you have a positive front half and a negative back half, but we have a lot of molecules that do not form from ions. Many compounds are formed by a different method than the transfer of electrons. They're formed by the sharing of electrons. We call them covalent bonds. And they do not form the crystal lattice that ions do. Instead, they move around as individual units, as molecules. Examples that you're familiar with are water and carbon dioxide, but there's a huge number of other molecules around. For instance, glucose and DNA and proteins, hemoglobin in your blood and things like that. They're all made with covalent bonds, and they move around as individual units, and that's what we're going to investigate now. The first ones that I'm going to introduce you to are the diatomic molecules. Now, any molecule that is made of two atoms is called a diatomic molecule. For instance, carbon monoxide is a diatomic molecule. But we're going to look at what are the diatomic elements. There are some elements that come always as two atoms bound together. Most of the elements in the periodic table can be taken from a sample, and theoretically individual atoms could be removed from those samples of the elements. If I were to take a sample of potassium, let's say, theoretically I could remove one atom of potassium from its sample. There are some elements in which you cannot do that. If I have a sample of oxygen and I somehow grab a hold of one of the oxygen atoms in there and try to remove it from the rest of the oxygen, what I will find is there is another oxygen attached to it. They're almost like Twinkies. They only come bound together in a package. These elements that come as diatomic molecules are hydrogen, that's way over there on the upper left, and it's over there with the metals because it does have some behavior like the alkali metals, but it is a covalent element. It comes as a diatomic molecule, and it is not considered to be a metal. The other elements that come as diatomic molecules are, look over there at number 7, nitrogen. That starts the diatomic molecules, and you can see it goes to oxygen 8, fluorine 9, then down to chlorine 17, bromine 35, and then iodine 53. The elements nitrogen through fluorine down to iodine, you notice it forms a little 7 in the corner there. And it's easy to remember their location, which are the diatomic molecules, by that little 7 that they form in the corner, plus hydrogen way over there at the top of the alkali metals. Whenever you see these in reactions, if the element is not in a compound with other elements, they will be as a pure element, but written as a diatomic molecule. And we will see that in the future. For instance, hydrogen will react with oxygen to make water. Hydrogen is written in that reaction as a diatomic molecule. Oxygen is written in that reaction as a diatomic molecule. So, but that's when they're the pure elements. When they're in compounds, they can come as individual atoms and recombine and form any number of hydrogens or oxygens, for instance, in other molecules. So how is it that two hydrogens bond together? They certainly do not exchange electrons so that one makes a hydrogen positive cation and the other a hydrogen negative cation, because they have the same characteristics. One isn't stronger at pulling electrons away from the other. So they have to be doing something different. So what we're going to do is essentially allow the two atoms to come close to each other and examine what can they be doing. If we move these two atoms closer so that their electron clouds can overlap, we then see that the electrons from one can actually be in the cloud of the electrons of the other. This actually happens so that the two electrons are actually spending time on both atoms. The hydrogen on the left now has two electrons in its 1s sublevel, and so it now has 1s2 electron configuration, and that is a stable electron configuration. Likewise, the one on the right is the same, 2 electrons in 1s. It now has stability. This is what's called covalent bonding. Covalent bonding is when electrons spend time on both atoms, and we call it sharing. Through the sharing of electrons, each hydrogen has a 1s2 structure, which gives it stability. Each electron is attracted to both nuclei and basically moves around both nuclei, wrapping the two positive nuclei in negative charge. This effectively pulls the two nuclei together. You have on the left the positive nuclei between two negative electrons pulling together the other nucleus towards the center. So basically you have the two negative electrons in the middle drawing the two positive nuclei towards the center. The electrons have a huge probability of being found between the two nuclei, and that is what causes bonding. Well, we just looked at hydrogen in a very simple way. What we're going to do is use Lewis dot structures now to look at other atoms. So how does fluorine bond in a fluorine diatomic molecule? Well, we have to look at the valence shell. And at this point in time now, we're only going to be looking at valence electrons because the core electrons really do not participate in bonding at all. It's all valence electrons, at least when we're using the valence bond theory. Okay, so the Lewis dot structure of fluorine is shown here. It's S2P7, so it has 7 electrons in its valence shell. If I bring these two fluorines with 7 electrons close to each other so that they can have sharing of electrons or orbital overlap, you can see that the fluorines can share these two unpaired electrons. If I redraw it so that the two electrons are between the two nuclei, as we usually do like this, then you can see the fluorine on the left has 8 electrons around it. It's S2P6, stable. We call that an octet. The fluorine on the right has 8 electrons around it with an S2P6 arrangement. That's stable, and we call that an octet. So we now have a stable structure between both. We have a stable structure, and both atoms each now have an octet and are stable from the sharing of electrons.